Hi everyone, am I audible? Okay, thank you. So we'll just wait for a couple of more minutes and I think then we can start. Waiting for other students to join and then we'll start. So it's already 3:05. I think we should start. Some people are joining, but I'll admit them anyways. So welcome. I welcome you all to this live session 2, basically problem solving session for the course CMOS Digital VLSI Design. My name is Musab Rafiq. I'm a PMR scholar in the Department of Electrical Engineering at IIT Kanpur. So the course is taught by Professor Sudev Dasgupta from IIT Roorkee, and this is live session 2, as I already advised. Now, towards the contents of this week, so the problems will be pertaining to week 2 content. So, uh, we'll study or we'll discuss problems related to CMOS inverter basics and some problems related to power analysis, but mostly it will be concentrated on CMOS inverter. I try to put in some problems of logical effort, but I see that it will be discussed primarily in week 7 or 6. So I have omitted them right now, but towards the end of this course, we'll definitely discuss those problems in today's live session. I haven't put those because I need to go according to the content of the particular week and as per the uh, assignment, the problems, how are they designed in the assignment. I'll mostly follow that routine. Now, the guidelines. So, some of you are aware of these guidelines, but I'm bound to repeat them every time. So, first of all, the guideline number one is the authentic username. Participants with fictitious or inappropriate usernames will not be added to the session. Number two is camera and microphone etiquette. At all the time, please keep your microphone on mute and camera turned off. However, if you want to ask a doubt, you can raise your hand and or you can directly type in the chat box. But if you want to ask your doubts by using the microphone, you will raise your hand and I'll ask you at appropriate time to ask your doubts. And regarding the questions and doubts, so how I approach the problems is first I'll show the problems, then I'll show the solution to it, and once I have shown the solution, I'll give you some time to asking your doubts. If you have your doubts, you can use the chat box or you can raise your hand. And there are some problems in the session that I kept like first you'll solve them and then I'll show the solution. And also the session is being recorded, so the link will be made available to you as you have already been shared that weekly log sheet where you will find the contents of this live session and previous live sessions as well as the links to the YouTube videos. And also occasionally there might be some breaks in case the session goes lengthy. And if you have some question, you will always feel free to reach out via email. Now, I hope that's clear with all of you. So let's start with the first question. In fact, it's the question from last week, which I had given you as an homework, or you can say I already gave you some hints related to this question because it was already being discussed. Just a second, I'll admit some students. So we have this question here, which was a homework assignment for the last week session. So the idea was to find the switching threshold of the CMOS inverter using the following data. It followed the same pattern as the previous question that we had that last time. So has anyone solved it? If yes, please type in your answer. Otherwise, I'll show the solution. I'll show the solution anyways, but has anyone solved it? If yes, you can type your answers in the chat box. I'll then proceed with the solution. We'll just go quickly over this question because it's from last week. I don't want to spend much time on this. Okay. Anyways, if you haven't done it, no worries. You can always take a look at last week's sessions recording and check those questions. But still, I'll show the solution. I'll go over it quickly because it's been already discussed last time. So we need to find the switching threshold, which is defined by this Vm, which is equal to Vtn plus Vd sat n by 2 plus R times Vt Vdd plus Vtp plus Vd sat p by 2. R is defined as the ratio of Kp by Kn times Vd sat p by Vd sat n. I'll only concentrate on magnitudes, the sign I won't take here. So Kp will be equal to W by L P times Kp bar by W by L n Kn prime multiplied by Vd sat p by Vd sat n. This is your process transconductance, this is your device transconductance, as already discussed last time. Now plugging the values we have here, W by LP and W by L are equal, so it will cancel out. Kp prime is equal to 30 into 10 raised power minus 6, and this is equal to 115 into 10 raised power minus 6. Vd sat P is minus 1, but I'll only take magnitudes because I have also taken positive for this Kp, and divided by Vd sat n, that is 0.63. So if you do the maths, it comes out to be 0.41. R comes out to be 0.41. Kindly cross check it. Now plugging this VR value in 1, so what we'll have here is, and also the other variables, so Vtn is 0.43, Vd sat n is 0.63, so divided by 2, plus R is 0.41, and this was, nobody corrected me, this was 1 plus R, divided by 1 plus R. So 0.41, and VDD is how much? 2.5, plus VTP is minus 0.4 volts. VTP is minus 0.4 volts, and VD sat P is how much? Minus 1 by 2 divided by 1 plus 0.41. So if you do the maths, it comes out to be 0.745 plus 0.41 multiplied by 1.6 divided by 1.41, and it comes out to be 1.401 divided by 1.41, which is equal to 0.993 volts. So Vm is equal to 0.993 volts. I hope you also got the same answer if you had done it. So this was exactly like the question we did last time. So let's move forward to the first question of today's live session, which says that the voltage transfer characteristics of a of a logic inverter are shown in figure 1. So we are given this VTC shown in figure 1, and all the values are in volt. So what we are required to find is the noise margins, the gain in the transition region, and inverter threshold from the figure itself. So this is the voltage transfer characteristics, basically the output voltage versus the input voltage. So how will we start first? So we'll start by marking VOH, that is V output high, which is equal to how much? Anyone in the chat box? VOH is how much? 4. Thank you. 4 volts. Then we have VOL, that is how much? 0.5 volts, correct. Then I have VIL, that is how much? Thank you. It's 1.5. And finally we have VIH, which is 2.5 volts. Please turn off your microphones. If you want to ask some doubts, I'll give you time at that time. Now we have noise margin high, which is equal to VOH minus VIH, that is equal to 4 minus 2.5, that is equal to 1.5 volts. Then we have noise margin low, which is equal to VIL minus VOL, that is equal to 1.5 minus 0.5, that is equal to 1 volts, right? And the noise margin will then be equal to how much? Noise margin will be equal to how much is noise margin equal to? This was noise margin high, this was noise margin low. How much will be noise margin equal to? Are you sure, or is it minimum of NMH or NML? So So noise margin will be equal to minimum of noise margin high comma noise margin low. What is minimum of these two? It's 1 volt. So one minimum of 1.5 comma 1 is 1 volt. If there are any doubts, you can refer to the lecture or the text. Now part 2 asks us to find the gain in the transition region, that is this region. So to find the gain in the transition region, we will use piecewise linear approximation. And how will you do it? We will mark this point and this point, and we will have our equation like this: V0 minus, so we'll have V0 minus 4 equal to, sorry, let me just rephrase it. We'll have gain like this. So gain will be simply equal to slope, right? So gain will be equal to VOH, that is this point, minus VOL, that is this point, divided by VIL, that is this point, minus VIH, that is this point. So it will be equal to 4 minus 0.5, and VIL is how much? 1.5 minus 2.5. So gain will be equal to minus 3.5. Now the third part is inverter's threshold, that is basically this point where VO is equal to VI. So inverter threshold will be equal to, we'll use a piecewise linear approximation here as well. So we have V0 minus 4 equal to minus 3.5 Vi minus 1.5. At Vm we have V0 equal to Vi equal to Vm. Then we'll have Vm minus 4 equal to minus 3.5 Vm minus 1.5. Simplify it at your end. Just simplify it. I'll just wait for a couple of 10 to 30 seconds. Simplify it. I want you guys to simplify it or do the calculations at your end. So what we can have here is, it will be Vm equal to 4 plus 3.5 multiplied by 1.5 divided by 3.5 plus 1, and it comes out to be 2.055 volts. Can you confirm this? Can you cross check it please, whether you also get the same answer? You also got the same answer? Yeah, thank you. So what we saw here is, we first computed the noise margins from the figure, then we did the gain part right here, and finally we had the threshold, switching threshold. Any doubts? Please ask, otherwise we'll move to question number 2. Okay, so part 3 is basically we need to find this point Vm. So I have used this piecewise linear approximation. So I have taken this point and at this point, so I have written that thing only. So V0 here, V0 minus 4 equal to minus 3.5 Vi minus 1.5. So basically y is equal to mx plus c, or y2 minus y minus y1 is equal to m times x minus x1. So from that part I put V0 equal to Vi equal to Vm, because at switching threshold my input and output are equal. So I put this value in this and I did the maths, then did the calculation part. I got Vm equal to 4 plus 3.5 multiplied by 1.5 divided by 3.5 plus 1, and finally I got the answer as 2.055 volts. Now someone has requested about the part 2 part where I need to find this gain. Basically gain is the slope of this transition region. So gain is equal to taking this point, that is VOH, and this point, that is VOL, VOH minus VOL, that is Y2 minus Y1 divided by X2, that is 1.5 minus VIH, that is 2.5. That's what I have written here. 4 minus zero point 0.5 and 1.5 minus 2.5, and when you once you do the maths, you will get G equal to minus 3.5 volts. Is it clear? So now let's move to what should I say, question number two of today's live session. So I have marked this question. So what I want is you guys to solve it first, and then I'll show the solution. Just attempt it, try to solve it. I'll just give you a couple of minutes, maybe 2 to 3 minutes to solve it. So the question states that an ideal two switch inverter has voltage transfer characteristics as shown in figure 2, that is here. Assume VDD equal to 5 volts, R1 equal to 1 kilo ohm, R off equal to 10 mega ohm for both the switches. So once one of the devices on, it has R on equal to 1 kilo ohm, and other device has R off equal to 10 mega ohm. And in the other case, if that one is on, it has R on equal to 1 kilo ohm, and R off, other devices R off equal to 10 mega ohm for both the switches. So it's symmetric kind of a thing. So then what's required is you need to find the VOH, you need to find the VOL and the noise margin given VIH and VIL equal to VDD by 2. I'll just wait for a couple of minutes. You guys can solve and type in your answers. Then I'll show the solution. Has anyone solved it? If not, let me just show the solution, or you can try it your end as well while I'm showing the solution. So what we have is we have the ideal two switch inverter, basically one block here and other block here, one switch here and other switch here. This is VDD, this is ground, and this is V out. So now we have to assume VDD equal to 5 volt, R on equal to 1 kilo ohm, and R off equal to 10 mega ohm for both the switches, right? So what we have here is we need to find VOH, VOL, and noise margins. So first we need to find VOH. The part is VOH. So VOH can be found when V in is pretty low, right? So when V in is low, my pull up network is on, is having R on resistance, and my pull down network is off, so it is having R off resistance, and this here will be VOH, right? So if you resistor divider, I'll have VOH equal to VDD times R on, sorry, VDD times R off by R on plus R off, basically the voltage divider between these two. Once I plug the value, so VDD is equal to 5, R off is how much? 10 mega ohm. So 10 and 1 mega ohm is 10 raised to power 6 ohms. So it will be 10 into 10 raised to power 6. So that is 10 raised to power 7. Just write directly 10 raised to power 7 divided by 10 raised to power 3, because 1 kilo ohm is 10 raised to power 3 and 10 raised to power 7. Once you do the maths, it will comes out to be 4.995 volts, which is approximately equal to 5 volts. Now we need to find uh, what we need to find is VOL. So VOL will be there when output, sorry, when input is very high. So that will give us the condition like this, where my pull up network is off and my pull down network is on, and this here will be VOL. So VOL will be equal to VDD times R on by R on plus R off, right? And once you plug these values, so 5 into 10 raised to power 3 divided by 10 raised to power 7 plus 10 raised to power 3, it comes out to be approximately equal to 0.5 millivolts. Kindly check the numbers at your end. So we have the VOH with us, we have the VOL with us. Now we need to find the noise margin. So noise margin high we'll first find, which is equal to VOH minus VIH. So VOH is approximately equal to 5 volts, and VIH is equal to VDD by 2, that is 5 by 2 volts, so equal to 5 minus 2.5, it's approximately equal to 2.5 volts, right? This was noise margin high. Now noise margin low is equal to VIL minus VOL. VIL is also VDD by 2, that is 5 by 2, minus VOL is 0.5 millivolts, so it comes out to be approximately equal to 2.49995 volts, right? If you do the exact number for this as well, it comes out to be, let's take the exact number rather than doing the approximation. It comes out to be 4.995, and this also here will change. It comes out to be 4.995 minus this, and it also comes out to be 4.995 volts. So this was noise margin high, noise margin low, and noise margin will also be equal to 2.4995 volts. So is this clear? No, it's not for every time. So first take this case. First of all, just clear in your mind, here it's written a two switch inverter, right? So you can't say a PMOS or an NMOS. The condition was two switch inverter. We have the up pull up device, we have a pull down device, or you can say a pull up switch or a pull down switch, and both of them are either one of them is on and other one is off. So once one is on, it has a R on resistance of 1 kilo ohm, and the other has a R of resistance of 10 mega ohm. In this case, this device was on, the pull up device was on, having R on resistance equal to 10k, sorry 1k, and this was off, having a R of resistance equal to 10 mega ohm. In the other case, this was off. So this was having a R of resistance of 1 mega ohm and 10 mega ohm, and this was having a R on resistance, that is a pull down network, was having an R on resistance of 1 kilo ohm. So you can't just say the PMOS is 1 kilo ohm for every time. It's when it's on and when it's off. So when my pull-up device is on, it's having on resistance of 1k. When it's off, it's having a off resistance of 10 mega ohm. Similarly for pull-down device, when it's off, it's having a R on resistance of 1 kilo ohm, and when it's off, it's having a R of resistance of 10 mega ohm. I hope that's clear, right? Now, question number 3. It asks us, find the optimal size of inverter A2 and A3 in the following inverter chain in terms of the size of A1. Consider the input capacitance A1 to be C1 and load capacitance 27 times C1. So I think this type of questions you have already seen in your lecture sites as well. So what we'll have here is, we need have number of stages, that is n equal to how much? 3. We'll just first write the values we have, and we have CL by C1 given to be 27, and there is a particular name associated with this CL by C1. It's represented by a particular letter and it has a particular name. What is it called? CL by C1 is represented by what? In the chat box, please. F. Is it small or capital? There's a difference between small f and, yes, exactly. It's a capital F, and it has a particular name as well, right? What is it called? It's called overall effective fan out. Now we have this thing equal to, now small f is equal to f raised power 1 by n, right? So f is 27 and my number of stages is 3, so it's 1 by 3, and f is equal to, small f is called effective fan out, so f is equal to 3. This CL by C1 has to be distributed equally across n stages. Now we have the overall effective fan out equal to be 3. So that means A2 by A1 is how much? Equal to F. That implies A2 is equal to, A2 by A1 is equal to 3. That implies A2 is equal to thrice A1. This is one condition. And also A3 by A2 is also equal to F. That is equal to A3 by A2 equal to 3. That implies A3 is equal to thrice A2. And A2 is equal to thrice A1. That implies A3 is equal to 9 times A1. So A3 is equal to 9 times A1 and A2 is equal to 3 times A1. That is option A. That is the correct answer. Is that clear? Now, moving to question 4 of, no, I can't. Sorry. Maybe, so what I'm supposed to do is, this is an clear guidelines. In fact, I discussed this last time as well. I will show the questions that are in accordance to the assignment problems or somewhat related to the assignment problems, or maybe slightly tougher or easier problems than assignment problems. But I can't show assignment problems, the exact assignment problems here. And that is the guideline that has been given to us, and I have typically followed that guidelines over the last 3 years. If you are facing some issues with the assignment, after the due date is passed, you can bring up that question. Even after they provide the solutions as well, right? Even after the solution is provided, you have some doubts, you can always reach out to me in the live session, and at that time, I'll try to clear your doubts. Is that clear? I hope that's clear with everyone, right? Now, moving forward to this question number 4 of today's live session. So states that for a combinational logic gate, alpha equal to 0.2, load capacitance equal to 150 femtofarad, and VD equal to 2 volt, and clock frequency equal to 2 gigahertz. Calculate the circuit power dissipation. Calculate the circuit power dissipation. VDD equal to 1.5 volts. So we directly use the formula which says that power dissipated is equal to CL VDD square alpha times F. So here I want to make one note which you guys should remember. I think in the solution of previous year assignments or the maybe some notes, uh, it was written half of CL VDD square alpha F, but I checked it with some sources, but I found that it's equal to CL VDD square alpha F. So what you can do is you can raise this query in the forum and cross check with the course TA maybe or professor. If that's not possible, maybe in the next lecture I'll try to bring some explanations, or maybe I'll take this issue with the professor and you'll get the answer correct. But so far we'll just consider CLVDD square alpha F, not half. So plugging the values. So after we plug the value, so it's 150 times VDD is how much? Just a second, just a second. Something happened. Okay. So it's CL VDD square alpha. CL is 150 times 10 raised to power minus 15. VDD is 2 raised square. Alpha is 0.2 and F is 2 gigahertz. So 2 into 10 raised to power how much? 9. And once you do the math, it comes out to be 250 microwatt. Right? You can cross check the numbers. Similarly, when VDD equal to 1.5 volts, PD is equal to 150 into 10 raised to power minus 15, 1.5 square multiplied by zero point 0.2 multiplied by 2 into 10 raised to power 9. It comes out to be 135 microwatt. So you can see by with scaling the supply voltage from 2 volts to 1.5 volt, we have a power savings of nearly 100 microwatt, which is very huge. So just a question to you guys, which you can look at your end. No need to answer right now. Since we saw that with scaling, our VDD also scales, but we only scale VDD up to a certain point. The VDD scaling is only done up to a certain point. We can't scale VDD in necessarily, means we can't go on and on and on for VDD scaling. There is a particular reason where VDD scaling is has a particular limit. What is that limit, and what is the reason that we have to set certain limit for VDD scaling? So VDD is greater than some particular limit. Try to look at that and see for the answers. Now we have question number 5 of today's live session. Not really. So if you see with each technology node, my VDD was also scaled, right? And it was able to reproduce my VTC exactly. My CMOS characteristics were being reproduced. But still, we said we can't go below a certain limit because of some limitations. What I really want is to look at those limitations. What are those limitations? And why VDD can't be scaled continuously. It has a particular limit up to which we can go. The answer is in Rabai. Uh, I think technology. Yeah, 1.84 volt, and if you take 14 nanometer technology, or it is zero point 0.8, and in 7, I think it's zero point 0.7 volt. But it still has a limit. I mean to say, it still has a limit. You can't go and go on, go and go on forever. There is a limit. Refer to Rabai, you'll find the answer. Rabai chapter 5, where the voltage transfer characteristics are being discussed and followed by the scaling part. There it's written why we can't go. Just a simple explanation. It's not that complicated. Now question 5, it says that for a 180 nanometer technology node, the transistor parameters are as follows. L min is equal to 130 nanometer W min is equal to 130 nanometer, Kn prime is equal to 400 microampere volt raised to minus 2, Kp prime is equal to 200. My Vtn is equal to mod of Vtp 0.3 volt, and channel length modulation parameter lambda is equal to 0.00212 volt inverse. The supply voltage VDD is 1.8 volts. A CMOS inverter with symmetric VTC is designed with a minimum sized P MOSFET. Assume that the load capacitance is dominated by extrinsic capacitance and CL is equal to 1 picofarad. By the way, what is meant by extrinsic capacitance? Anyone? You can say the output capacitance, the load capacitance is uh, not coming out from itself. I mean to say not coming out from the inverter one or the particular gate itself. Some external parameters, some external things. So you are referring to a chain of inverters. You can say that capacitance is coming out of it from the second inverter, or the wire capacitance, the parasitic capacitance. You can say that. Now we need to estimate the equivalent resistance of N MOSFET at time t equal to 0 after the application of step input and t equal to 50 seconds, and also find the propagation time high to low and propagation delay. So we have a CMOS inverter which typically looks like this. Yeah, output, we have input. This is minimum size, so W by L is minimum sized, and this will have W equal to W min and L equal to half of L min, because the VTC is symmetric, that's why. And question is given as PMOS to be minimum sized. Following this fact, I have R equivalent of 0 plus, so I need to find the equivalent resistance at 0 plus. So it will simply, for NMOS, so it will simply be equal to VDS of 0 plus divided by IDS at 0 plus. So VDS at 0 plus will be equal to VDD, and IDS we need to find. And if you look at this time, my NMOS will be in saturation because VGS is greater than VT and VDS equal to VDD, that is obviously greater than VGS minus VT. So I can write ID equal to mu n Cox divided by 2 W by L times VDD minus VTN square times 1 plus lambda VDS, which is a channel length part, channel length modulation part, and this is equal to half of mu n is given to be mu n Cox is given to be 400, and then W by L I can write 1 by 2, and VDD minus VDD is how much? 1.8 minus VDD is 0.3 square times 1 plus lambda is 0.02 and VDS is 1.8. If you do the maths, ID comes out to be 233.1 into 10 raised to power minus 6, that is equal to 233 microampere, and that is equal to 0.233 milliamps. So R equivalent at 0 plus will be equal to 1.8 divided by 0.233, so it will be equal to 2.72 kilo ohms. Now at t equal to 50%, R equivalent 50% will be equal to VDS of 50% divided by IDS of 50%. So in that case, I will have my NMOS like this, where this is VDD by 2. So in this case, my NMOS is in linear region, right? So my IDS will be written like this: mu n Cox W by L VGS minus VT times VDS minus VDS square by 2 multiplied by 1 plus lambda VDS. I won't go into the calculation part of it. I'll just write the answer directly. So it is 190. Just wait a second. Something happened to this. So IDS is equal to 192 microamperes, that is equal to 0.192 milliamps, and R equivalent, I'll just continue here. So IDS at 50% will be equal to 0.192 milliamps, and R equivalent will be equal to zero point 0.9, that is VDD by 2 divided by 0.1924. That is how much it comes out to be, 4.678 kilo ohms. Now the total R equivalent is basically average of the two resistances, that is R equal to 0 plus, R equivalent at 0 plus, and R equal to 50 plus. So it is R equivalent at 0 plus plus R equivalent at 50% divided by 2. So it is 7.72 plus 4.678 divided by 2. It comes out to be 6.2 kilo ohms. And my TP high to low will be equal to 0.69 times R equivalent times CL. So it is 0.69 times R equivalent is 6.2 K times CL is how much? CL is 1 picofarad, that is 10 raised to power minus 12. And if you do the calculation part, it comes out to be 4.278 nanoseconds. Also given was the emitter is symmetric, so that implies TPHL is equal to TPLH, so that is equal to 4.278 nanoseconds, and my TP, that is the propagation delay, will be equal to TPHL plus TPLH divided by 2, that is 4.278 itself. So this was my propagation delay. Any doubts in this question? Kindly write in the chat box if you have any doubts. If not, we can move forward to this. Yeah, I thought this question will come up. Just check the question. The devices, the CMOS inverter characteristics are symmetric, and given is my PMOS is how much? My PMOS is minimum size. So my W and L for the PMOS is fixed. Now to make it symmetric, L of this, what should I say, needs to be changed, and you can figure it out from this y divided by 2 factor, because kn prime by kp prime is equal to 400 by 200, it comes out to be 2. So my L gets divided by 2. Characteristics were symmetric, PMOS was minimum size, that's why L of NMOS needed to be changed to half to get the characteristics symmetric, to get the delays equal, right? Now I have this question which I like you guys to first answer to me. So what is this? VTC of a inverter, right? So can you write What are the things you can extract from a VTC? Things you can extract from a VTC. What information does it tell to you? Noise margin, region of operations, right? Gain also, cutoff and saturation. Gain also, right? I have this question in digital applications. We don't bias our transistor in this region, right? We don't bias our transistor in this region in digital applications, this transition region. Why? Due to high uncertainty. High uncertainty, well taken, but high uncertainty of what? It's not zero or one. Because the operation might not be reliable. Yeah, exactly. Unstable was the word I was looking for. Yeah, that's all. So now I have this question. So here at this point, can you tell me what is the region of operation for PMOS? Linear or resistor? And what about NMOS? Off or cut off? Right. At this point, what is the region of operation for PMOS? Linear or resistance. And NMOS? NMOS? Correct. Saturation. We will have one more point here where V0 equal to Vi. What is this point called? What is this point called? Threshold point or tripping point of inverter. And what are the regions of operation for PMOS here? And NMOS? Yes, both are in saturation. What about this point? What is PMOS here? I'm getting mixed answers. Anyone? Yes, it's saturation. And NMOS? Linear, correct. What about here? PMOS? Off. And NMOS? Linear and resistor. So I would like one of you to answer a student why NMOS is in saturation here. Can anyone answer in the chat box why NMOS is in saturation here? Exactly. Because VDS is greater than VGS minus VT and also VGS is greater than VT. Not forget this condition. VGS is greater than VT and VDS is greater than VGS minus VT. Now building on this, uh, I would like you guys to solve this question and give me the answers in 2 to 3 minutes. I think we have done many questions based on the VTC and this is also one of them. So the VTC of an arbitrary CMOS inverter is shown in figure Q1. So here is the figure. So you need to determine the VOH the VOL, the VIL, and the VH of the inverter. So let's do it simultaneously. Tell me what is the VOH equal to? What is VOH equal to? Correct, 2 volts. What is VOL equal to? Anyone? What is VOL equal to? Anyone else? What is VOL equal to? Nothing to do with the electronics part, just a simple geometry part. VOL equal to zero point 0.2 volts. Here is a line that is going as V out equal to V in, and this intersection point will give me the VOL. Got it? Following the same lines, what is VIL equal to? So let me just explain it once. You see this line? What is this? V out equal to V in, and you need to find this point. This point. So the intersection of this is V out equal to V in. So if this is zero point 0.2, this is also zero point 0.2. Got it? Now VIL is zero point 0.8 volts as rightly said by one of the student. What is VIH equal to? VIH equal to 1.7 volts. So this was VIH VOL, and what is the switching threshold equal to? 1.2 volts. What is gain equal to? Anyone? Has anyone computed the gain? We did, our first question was exactly like this. Now you have all the values. What is gain equal to? Or should I say gain of the inverter in the transition region? I have to be more precise. Gain is minus zero point 0.2. So take this point and take this point. So it is 2 minus zero point 0.2 divided by zero point 0.8 minus 1.7, right? So this is 1.8 divided by minus zero point 0.9, so it is minus 2. Gain is minus 2. And noise margin high is equal to VOH minus VIH, that is 2 minus 1.7, that is 0.3, and noise margin low is equal to VIL minus VOL, that is zero point 0.8 minus zero point 0.2, that is 0.6 volt. I hope this was clear. Now I have this question. It states that in the inverter figure 2, assume that the switches are ideal and operates instantaneously. So it's instantaneous operation that we are having. And output has a load capacitance of 1 picofarad. If Vi, that is my input, rises from 0 to 5 volt as a step, find the propagation delay and transition time. And the second case is if Vi falls from 5 to 0 volt, find the propagation delay and the transition time. So we'll and values we have to take from the starting question 2. So this was here. I only need two values from there, that is R on and R off. So that was 10k and 1k and 10k. Sorry, 1k and 10m. So R on was 10 1k and R off was 10 mega. Now I have my first condition where my input goes abruptly to 5 volts from 0 to 5 volts. This is Vi. Sorry about that, there is some issue with PowerPoint, it happens sometimes. So it goes from 0 to 1.5 volts, right? This is VDD. So V0 of 0 minus is how much? V0 of 0 minus is how much? My output voltage at 0 minus will be how much? If my input is going from 0 to 5, what would be my output voltage as exactly? It will be no, not 0. V0, I'm talking about the output voltage. So I'll have something like this. R off, R on. This is case that is happening after 0 plus. What is the case at 0 minus? What is V0 at 0 minus? So my input voltage goes like this. Just before 0, what will be the output voltage? V0 at 0 minus will be equal to VDD, correct. That is 5 volts. And from the network analysis, now you take this picture. I'll have this R off and R on. From network analysis, you will have V0 at 0 plus will be equal to V0 at infinity plus V0 at 0 minus minus V0 at infinity e raised power t minus tau. I won't go into the details of it. You guys are very familiar with the network analysis part. Now, what is V0 at infinity? Can anyone tell me what is V0 of infinity? The steady state value. What will be that? V0 of infinity. Output voltage at after some, yes, exactly 0 volts. And V0 of 0 minus was 5. This is minus 0 e raised power minus t by tau. So it is my V0 at 0 plus will be equal to 5 e raised power minus t by tau. Tau is equal to R equivalent CL, right? My tau is equal to R equivalent CL. R equivalent I will take as R equivalent is equal to R on in parallel with R off. So that is 1k in parallel with 1 mega, that is approximately equal to 1 kilo ohm. I have taken this parallel because I'll consider this VDD part to be as a AC ground because it's changing instantaneously in that part. So I have taken it to be as a AC ground, and what I will have here is my R equivalent will be equal to R on in parallel with R off. So 1k in parallel with 10 mega ohm. So you know that when a very high resistance is in parallel with a very low resistance, it's the low resistance that dominates. So R on in parallel with R off is equal to R on approximately. So that's what I have written here. So it is equal to RK will be equal to 10 raised power 3. CL is how much? 1 picofarad. Yeah, 10 raised power minus 12. So my tau will be equal to 1 nanoseconds, right? Now I have tau with me. I'll just plug the value of tau in here. So, oh no, not right now. So now what I need to find is the propagation delay, that is TP high to low. So TP high to low means V0 of t. I need to find out the time at which my output is 50% of my input. So that's how we define the propagation delay, right? High to low. When my output is 50%, my input has changed to 50%, my output has changed to 50%. That time difference between them is my propagation delay. So V out of t is equal to VDD by 2. I need to find out the time when my output changes to 2.5 volts. So I'll write this V out of t here. So 2.5 is equal to 5 e raised power minus TPHL by tau, that is 1 nano, and that implies TPHL is equal to 10 raised power minus 9 ln of 2, and it is equal to 0.69 0.69, how much is it? 0.69 nanoseconds, right? Now just a second. Now we'll do the part 2 of it. We need to find the transition time. So transition time is defined when my output goes from, so to find the transition time, it is basically time taken from V0 equal to 4.5 volts to V0 equal to 0.5 volts. Can anyone tell me what are these 2 points? Why I've taken 4.5 volt and 0.5 volts? What does 4.5 volt? No, VOH is 5 volts and VOH is 5 volts. If you check, VOH is 5 volts. How do we define the transition time? Anyone? How do we define? Even I don't know the exact definition, but what I can tell you is it has something to do, yes, 90% to 10%. Exactly. So we'll have T1, that is at which output is equal to 4.5 volts. So we'll plug this value in equation. Let's just call this as equation 1. In equation 1, we'll have 4.5 is equal to 5 into e raised power minus t by tau. That implies T1. T1 is equal to minus tau ln of 0.9. T2 is equal to when V0 equal to 0.5 volts. That implies 0.5 is equal to 5 into e raised power minus T2 by tau. That implies T2 is equal to minus tau ln of 0.1, right? Now we need to find T2 minus T1. That implies tau ln of, if you do the maths, you'll get T2 minus T1 equal to tau of ln of 0.9 divided by 0.1, that is tau ln of 0.9. And when you plug the value of tau, that is, tau was how much? 1 nanoseconds. So this comes out to be 2.197 nanoseconds. Now the part 2 of it, where my input goes from 5 to 0 volts. So this is like this, Vi. My output changes from 5 to 0 volts. So it will be like this. My output circuitry will be like this. So here V0 of 0 minus is how much? V0 of 0 minus is how much? Anyone? What will be the V0 of 0 minus here? Yes, it will be 0. And what will be V0 of infinity? Correct. So that implies my V0 of t will be equal to V0 of infinity plus V0 of 0 minus minus V0 of infinity e raised power minus t by tau. Plugging these values, it will be 5 plus 0 minus 5 times e raised power minus t by tau. So it will be 5 times 1 minus e raised power minus t by tau. Now for propagation Tp low to high, I'll have V0 equal to VDD by 2, that is equal to 2.5. That implies 2.5. I'll plug this value in equation 2 now. V0 of t equal to 5 times 1 minus e raised power minus t by tau. So 2.5, I'll plug this value, is equal to 5 times 1 minus e raised power minus Tp low to high divided by tau. That if you do the maths correctly, it comes out to be 1 minus e raised power minus tp low to high equal to 0.5, and I'll skip some steps. Tp low to high equal to tau ln 2, it comes out to be 0.69 nanoseconds, right? Now we need to find the transition delays. So here transition delay will be when V0 changes from 0.5 volt to V0 equal to 4.5 volts. So at V0 we'll call T1, at V0 equal to 4.5 volt we'll call T2, and we'll use equation 2, which is here. When we use equation 2 for first case, so 0.5 volts equal to 5 times 1 minus e raised power minus T1 by tau, and T1 comes out to be minus tau times ln of 1 minus zero point 0.1, that is equal to minus tau times ln of 0.9. In the second case, it will be 4.5 times 5 times 1 minus e raised power minus T2 by tau. It comes out to be T2 comes out to be minus tau times ln of 1 minus 0.9, so it comes out to be minus tau times ln of 0.1. T2 minus T1, which is defined as transition time of low to high, comes out to be tau times ln of 0.9 minus tau times ln of 0.1, so it is tau times ln of 9, which is equal to 2.197 nanoseconds. Since the basically the device was symmetric, that's why the transition time and propagation time in both the cases came out to be similar. Any doubts? Now let's move forward to this question number 9. This we'll try to solve simultaneously. So part 2, yeah, you part 1 you got, part 1 was clear, right? Yeah. So in part 1, basically our input was going from low to high. In part 2, my input is going from high to low. So V0 0 minus, just before the step input is applied, my output will be 0 volts, right? And V0 of infinity will be 5 volts. Now using this equation, V0 of t equal to V0 of infinity plus V0 of 0 minus V0 of infinity multiplied by e raised power minus t by tau. And once you do the maths, it comes out to be V0 of t comes out to be 5 times 1 minus e raised power minus t by tau. Tau is same, this one. Now once I use this equation, I need to find the propagation delay when my low to high, basically when my output changes to from low to high. This point is basically the 50% value, and my output becomes VDD by 2. So when my output becomes VDD by 2, that is 2.5 volts, I'll put this value in equation 2, which is this, and I will have 2.5 equal to 5 times 1 minus e raised power minus t p low to high divided by tau. And once you do the math part of it, it comes out to be 1 minus e raised power minus tp low to high equal to 0.5, which is equal to tp low to high equal to tau times ln of 2, which is equal to 0.69 nanoseconds, because tau is 1 nanosecond itself, right? Now you need to find the transition time. The transition time is basically when your output changes from the 10% to 90%. 10% is 0.5 volts and 90% is 4.5 volts. So I'll mark this time instance at T1 and this time instance at T2. Now I'll use equation 2 again. So I'll have this part where T1 comes out to be minus tau times ln 9.9, and T2 comes out to be minus tau times ln of 0.1. I have used equation 2 and plugged 4.5 volt there and 0.5 volt here. Now then I will do the difference of these two, T2 minus T1, which is equal to the transition time. That comes out to be tau times ln of zero point 0.9 minus tau times ln of 0.1. Basically ln of a minus ln a minus ln b is equal to ln of a by b. So it comes out to be tau times ln 9. So it comes out to be 2.197 nanoseconds, right? Is that clear? Now let's do this part simultaneously. So fill in the blanks with appropriate expressions after equal to or symbols. So you have to fill in with the correct values, or you have to tell me whether it will be greater than some value or not. So let's take this one part first. Let's go step by step and let's label them part 2, part 3. So here the question asks what will be the output VOH. So we have to give the exact value since equal to sign is there. So what will be the VOH equal to here? Anyone? Anyone? What will be VOH equal to? It's pretty simple. So VOH is basically when V equal to V in equal to 0. Not exactly V, it will be VDD. I have not given any value, so forget the previous values. Every question will have different value, right? So it will be VDD minus something. Can you tell me what is that minus something? We have to find V out itself. So VOH is basically V out at V in equal to 0, right? So what is that? It is VTN. Can anyone tell me what is this? Yeah, I know it's NMOS, but it has a particular name. The configuration, this particular configuration has a name. A pull-up network is fine. Let's not confuse you. This is VDT. This is what is this thing? This is depletion and MOS. Can say that. Diode connected load. Have you heard of that? Diode connected. And what is the characteristics of this? What you can say from this? When gate and drain are short, uh, what will be the region of operation of the device? Exactly. So the device will be on as long as. So let's just make it like this. And I have my output capacitance here. So it will charge the capacitance VCL2. Up to what point it will charge the capacitor? Up to which voltage? not VDD. VDD minus VTN. Because once it becomes VDD minus VTN, my VGS becomes VDD minus VDD minus VTN. So my VGS then becomes VTN. And the moment it becomes slightly greater than this, my what will happen to my transistor? If VGS becomes less than VTN, what happens to the transistor? Exactly, it will turn off. That's why VOH will be equal to VDD minus VTN. And VOL will be greater than 0 volts. So for this, I'll have this figure for you where you can use the load line analysis to get the answer. So this is diode connected and MOSFET. So here I would like to thank my supervisor Professor Shubham Sai for providing access to the some of the lecture slides and questions that he had made in past, and also Professor Shafi Qureshi, the retired professor from IIT Kanpur. During my coursework here he taught me VLSI design, so I have taken some of the questions from assignments midsem and used them here. I'd like to thank them, both of them. So this is how you get the VTC of this thing. So here is your VTC less than VDD, and here is your VOL, and VTC is not ultra steep. So here you can see it, these points. Now what about this thing? What will be VOH equal to for this thing? Part 2. Yes, it will be VDD. And what will be VOL? Greater than? It will also be greater than 0 volts. And this thing will have steep characteristics, as you can see from here. This has a particular name and it's called pseudo NMOS logic. Here you can see. Now this part, I think all of you will guess this part correctly. What is VOH? What is VOL for this? Yes. And what is 1 and 2 signify here? No, no, 1 and 2. What does 1 and 2 signify here? NMOS and PMOS, W by L of NMOS and PMOS. Why do we make twice for PMOS? Why do we make PMOS 2 times? Because aspect ratio PMOS must be twice. But why? That's my question. To operate in VDD by 2. Exactly, symmetric characteristics. That's what I was looking for. Yeah, symmetric. To operate in VDD by 2, I got your point. You are taking this symmetric part. So we are paying the area penalty, rightly said. But what about the propagation delays? By increasing this, so what I'll suggest you guys, so you should look at Rabai and see this. We want, if symmetric criteria is our main part, we increase the W by L of PMOS. But sometimes symmetry is not our dictating part. So that times our delays are our dictating part, because once you increase the W by L of PMOS, my capacitances will increase, which will increase my delay, right? So, but sometimes when delay is our priority, we don't typically increase our width. So if you want to go and look for the applications or explanations for that part, You can always check the Rabai. This was just some side information. Now, a circuit designer has to consider alternatives for driving a load 25 times the input capacitance of a circuit. The first design uses one inverter, the second design uses two, and the third design uses three inverters in series. Which design is best and what is the minimum delay? So basically, it wants to drive a output load 25 times the input capacitance. So basically, CL by C in is equal to 25. And what is this thing equal to? We have already discussed this part. What is this equal to? F, capital F. Here I'll assume gamma equal to 1. Assumption. I'm assuming this. So when one inverter is used, TP is equal to, just a second, there's some issue with the PowerPoint, it's getting hanged. Just give me a second, the presentation is not working right now. Yeah, so gamma is equal to 1, that's the assumption that we have taken here. Then we, for one inverter case, my TP will be equal to TP0 n times 1 plus F by gamma, and F is equal to F raised power 1 by n. Here n equal to 1, so TP is equal to TP0 1 plus 25, so it equal to 26 times TP0. For I equal to 2, 2 stages, TP is equal to TP0 multiplied by 2 by 1 plus F, gamma is 1, so I have not written here, and F is equal to root 25, so TP is equal to TP0 times 2, 1 plus root 25 is 6, so it is 1 plus 5, so it is comes out to be 12 TPO. And for third case, it is TP equal to TP0 multiplied by 3, 1 plus cube root of 25, and if you do the math, it comes out to be 11.76 TP0. So if you can see in terms of propagation delay, the design with two inverters give me the, sorry, three inverters give me the least delay, but to get the area saving part, we'll choose this two inverter part, as it also gives me the area savings and delay is not deteriorated significantly. So we'll choose this part. Now the last question of today's live session, which states that a CMOS inverter operating at VDD of 2 volts and VSS of 0 volt has switching threshold of 1.54 volt. Plot accurately the VTC of inverter. So let's plot the VTC. So this is V out, this is V in. So what is my VOH? Anyone? What will be my VOH? 2 volts. So like this. And what will be my VOL? Now I have to plot VM. VM will be like this, and it is equal to 1.4 volts. Right. Now I have this part is done. Now I have assume inverter is driving a load capacitance of 1 picofarad, so that is equal to 10 raised power minus 12. We need to determine the dynamic power given the input square wave frequency of 100 kilohertz. So it will be CL VDD square F. So it is 10 raised power minus 12. VDD is how much? 2 volts. So 2 square minus F multiplied by F. So 100 K. So it comes out to be 4 into 10 raised power minus 7 watt. That is 0.4 microwatt. So what will be the static power dissipation from the source? Anyone? Why? You, if you want, you can unmute yourself and give the answer. Yes, only one of the transistors is off, and there is no direct path between the VDD and ground. Exactly. What is the output swing? What is the output swing of the circuit? From where to where my output swings? Just look at VDC, you can get the answer. Yes, 0 to 2 volts. So, I guess that was all for today's live session. If there are any doubts, please let me know. Otherwise, we can close the live session. So, thank you guys for joining. See you next time at this time.